So before we do some practice problems counting, we're gonna finish our what we need to finish. It'll take us a little bit to finish Catalan numbers. That's where we've been, where we were on Friday, on how does this go. So the first thing is to say we have a grid. This is 0, 0. This is M. So it's 1, 2, up to N, and this is 1, 2, up to N. So the question in here is how many paths from 0, 0 to, this is of course Mn, by a path only going up or right. So the allowed moves are to go up or to go right. When I talk about paths, I start in here. And I'm interested in things that are going right, up, 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 right, right, up, right, right, right. I'm interested in things that go that way. Say, don't go left or down. That's not allowed. How many such paths? That is the question here. How many? We solved this problem on Friday, and we said a path must be a sequence of how many moves total this path has to make. Any such path that starts from here to here has to make exactly m plus n moves. Because it has to make n move this way and n moves that way. And what is the choice? Why there are different paths? What makes it different from one path to the other? Yes?
You choose which ones are the good enough.
Right. We need to choose the right moves, for example, right? Which are m right moves. That's equivalent to choosing n up moves, because if I know which ones are up, the other ones will be to the right, right? So how many paths I have there? m plus n, choose m paths. Because I have m plus n moves, and what each path is defined by is which ones of these m plus n moves are the ones to the right, or are the ones go up, right? So now, that's what we've done on any grid. Like if you take a taxi in New York, which is a grid, Manhattan, and you only tell the taxi guy, I don't want you to go around, go right and up, or north and west, or something like this all the time. It's essentially that's how many ways to go. People still need their papers. How many people need their papers? Ask for the names and see who they are. Okay, so obviously if this is a grid of n by n, that's just a particular case. If this is a grid of n by n, then I'll have 2n choose n paths. Because m is equal to n, so I get exactly this. Now, in this grid, which is 5 by 5 in here, I have a particular problem. I draw this diagonal, and I'm asking This is total paths. But I'm asking for Catalan paths, which is not all of them. These paths that I'm interested in now are the ones that are always below diagonal. Below or equal. I don't mind a path touching the diagonal, I mind crossing it. So to be clear, I mean no crossing. Here's what I mean. Here's a path that's good. As long as it's under diagonal, it's gonna be fine. So I can touch here the diagonal, that's okay. Can touch it again, that's okay. As long as it stays, it doesn't cross the diagonal, that's okay. If this is blue, is good. It's a Catalan path. If that's obviously not all of them, right? There are some paths to go from 0, 0 to NN here that are crossing this diagonal. For example, here's a path that crosses the diagonal. It goes like this one, red. Be nice to see this. If you get any luck. So here's a path here that this is the crossing point. Clearly this path went up here. Can you guys see this color red on the board? So it clearly went up. Now suppose it goes more up, and even if it comes back to the diagonal, we still consider this path being a crossing. Now this path, I should say maybe that this is not red. This is okay, this part here. The red part is the ones after it crosses the diagonal. The moment it crosses the diagonal, that's not a good path. So red. Red means after diagonal crossing. So that's bad. Not bad, but a path that we don't want to count. How do we count only the blue path? So we know total is 2n choose n. Right? Because we said that. All the paths from here to here, 2n choose n. But we now want to say, okay, we only want the blue ones. How many paths are under the diagonal all the time? They never cross the diagonal. How do we do this? This requires a little trick. So, in order to count this, we're going to count this stuff. Like in many problems, in order to count the passwords that you want or the valid choices, we actually count the invalid choices. And then we make a subtraction. So we're going to count this. How we count it? We use that one-to-one mapping counting function. We're going to take every red path and map it to something. We say, here's the set of red paths. I'm going to put it here. These are the red paths. Set. And I'm going to build what we call a bijection. From here to another set. And then what we're going to say, if we have this bijection one-to-one mapping, we can count the red paths because the size of this set is going to be the size as of this, the same size as this set. Remember those kind of problems when we say if you build a one-to-one pairing function between set A and set B, and you want to count one of these sets, it has the same size as the other, so you can count the other set. That's our plan here. And what are we trying to count? Not the blue paths, the ones we really need. We're counting the red ones, the ones that are breaking the diagonal. So here's my bijection. I'm going to add a little bit to this grid here. And I'm going to say how far this these paths go. Let me see, I have it here somewhere. So I'm going to make one more row of the grid. And I'm going to ask, what is this? What is this point over here? What are the coordinates for this? So this is n, that's where all these paths end. But I'm adding one more row, and I'm going to say this is n minus 1. The first coordinate usually is the row count. So this is n minus 1, right? N plus 1. So this point has a less by 1 coordinate on this axis, but it has 1 coordinate extra on this axis. So what I'm going to do, my bijection is going to take any red path and it's going to do something magic. What's going to end up with the paths from 0, 0 to n minus 1, n plus 1. So I want to transform this red path, the one that crosses the diagonal, into a path from 0, 0, but not to here instead. Everybody follows me what I'm trying to do here? I want to build a one-to-one mapping between, I ignore the blue paths for now, only the red paths, and all the paths that go here. So what is my bijection? It's going to say reverse the red part of the path. So every red path must have a red part, right? Because that's why it's red. Which one is the red part? How did I define the red part of the path? After it crosses the diagonal all the way. Even if it comes back in, the path could come back into the good zone. Once it crosses the diagonal, it's red all the way to here. Okay? So the red part is the side that crosses diagonal. What my function does, it reverses the red side. What does reverse mean? Well, how do you reverse a path? What do you do? I guess there's a confusion maybe. Reverse doesn't mean you go backwards, because all paths go that way. It's reversing the moves. So let's see if we can do this. If the red path goes up, right, it actually starts from here. So it reverses the path after the first red move. So here's my bijection. Let's call it green. Green. I'm here. Now I want to reverse all those moves. All set?
Yeah.
Everybody got their papers?
Oh, the quiz, you?
Yeah.
Oh, I quiz.
There's still some left in there, maybe one person. Okay. So how do I reverse? If this red path used to go up, what do I do with my reversing function? I go to the right. So this is how it's going to go. This one goes to the right now. Now the next move was going right. What do I do?
Go up.
Up. The next move was going right, so I go up again. Next move was going up, so what do I do? Right. This one was going up, so I go do what? Right. This one was going now right, so I do what? Up. This one was going right, so I go what? Up. It's easy to prove, thank you. It's easy to prove that if this red path, once it crosses, see, I don't start on the diagonal the reversing process. Once the red path crosses, if the red ends up in here, it's a guaranteed thing that once I reverse the red moves, I'm going to end up in here. You can do that. It's a very simple calculation. Once you have one above the diagonal and you reverse it, you need so many moves and so many moves to get here. But if you do the opposite, you make these moves up, and the moves that you made up, you move to the right, you're going to end up here. Because those 2 points are symmetric to this point here. So if the one path ended up here, reversing it is going to be here. It's like a mirroring here. That's what happens. So now, why is this a bijection function? It's easy to see. What we did is a red path, any red path, will now correspond to this reverse path, green. How about the other way? If I take any path from here to here and reverse it, am I going to end up here? Yes. Any path that's from 0 to n to from here to here, if I reverse only the crossing after the diagonal crosses, I'm going to end up in here. But now, why is this any? This is not restricted. This is all paths. Because all these paths must cross the diagonal somewhere. Right? Every path from here to here at some point has to cross the diagonal up. Because if it be under the diagonal, it will never reach here. So the moment it crosses, I reverse it, I get to here, and I've got the red path because it already crossed the diagonal. So what I would like you to do after the midterm, this is not for the midterm, is to realize that this is a one-to-one mapping function. Every path that crosses the diagonal so has a red chunk, when I reverse it, I get also a red path, something across the diagonal, but ends up here. And it's a one-to-one correspondence between those two things. Can we count this? These are all the paths from 0, 0 to this spot. Can we count it? How many of them are there in this set? We just did this in a general case, right? How many paths are from 0, 0 to n minus 1 to n plus 1? Total, yes.
You can do choose n minus 1 plus n plus 1. And then you can choose
Either one of them.
4 of them. Yeah, n plus 1.
Either n minus 1 or n plus 1, right?
Yeah.
We already calculated the number of paths from 0, 0 to this spot. In general, in here, we said for any grid from 0, 0 to mn is n plus n choose n. So we know how many paths are in this set, which is all the paths. Those are not restricted, right? And we map those into the red ones. We say there's a mapping between every path from here and any one that's broken in the original problem. So thus we know the number of red paths. This is n plus 1 plus n minus 1. Choose n minus 1. That's the same way as 2n choose n minus 1. So can I now compute the blue paths? How many blue paths? That was my original problem. I didn't want to compute the red ones. I need to know how many blues are there. How do I do that?
Total minus red.
So what is it? So the blue paths are going to be 2n choose n minus how many red ones I've got. So that's 2n choose n minus 1. So how much is this? This is 2n factorial, n factorial times n factorial, right? Minus 2n factorial, n minus 1 factorial, n plus 1 factorial. If I do this as a common factor, so I would like to put this in the front, all 2n choose n, common factor, I get 1 minus 2n factorials in the front. This is n factorial in the front, so I have to have here an n up because this has only n minus 1 factorial, and an n plus 1 down because this, I took the n factorial out of it, but I still have an n plus 1 here. So now how much is this? This is 2n choose n times this fraction, if you compute it, is 1 over n plus 1. That is the Catalan number, Cn. There are many, many problems in graphs and combinatorics, computer science, that rely on this number calculation. This is only one such problem that says the answer to this, how many paths are from here to here that do not cross the diagonal, it's computed by counting the other paths that do cross the diagonal with a bijection function, and then counting this other set. And then if I want the blue ones, I take the difference between the total and the ones that don't satisfy. So that's good. What I would like to say now, here's how thinking in combinatorics go. Okay, I've got this problem. I've counted the paths from 0, 0 to n, it's this number. How about number of correct set of n parentheses? What does that mean? When you put parentheses, what is the rule? So this is open, 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 close, close, open again, close. Is that correct?
Yeah.
What's the rule? There's a rule, right? Yes.
Same number of opens closed.
But that's total. But can I have something like open, close, 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 open, open?
Open has to come first.
Right? This is also the same number open as close, but they kind of in the wrong order here. So what's the condition? The number of open eventually has to be equal to the number of close. That is n, because this is set of n parentheses. So it's n open and n close. But there is another condition much more important. At any time in this sequence, at any prefix of the sequence, what is the condition? Not just at the end. Anywhere you chop the sequence, you need to have a condition, somebody else, for this to be correct. What's the problem in here? Yes?
The number of opens has to be greater than the number of closed.
The number of open has to be not necessarily strictly greater, at least that many. You can't close more parentheses than you open so far. If you so far open 2 parentheses, you can only close 2. You need to open more parentheses before you close more parentheses, right? And that's not just at the end. At the end they're equal, anywhere in between. That's the rule of parentheses. You can't close more than you open. In any sort of algebra, doesn't matter if it's modular algebra or linear algebra or anything, multiplication of matrices. Anywhere you see parentheses, the rule is you can't close more parentheses than you opened on any prefix, right? Isn't this the same problem? Mentally, we need to build a one-to-one function.
Like if you think of open parentheses as moves to the right and closed parentheses moves up, it's the same problem. You can't go above the line. You can never have more ups than
What's the line? Where I touch the line means what?
same number of open and closed.
Same number of open close. What does it mean to break the line, to go over?
More closed than open.
Which is invalid. Every red path corresponds to some sort of sequence where you put more closed parentheses than you have open. That's why it's red. Right? There is a one-to-one analogy between those two problems. Formally, we call it a bijection. That says, what's my bijection? Every blue path is a correct sequence of parentheses. And every red path is what? Incorrect sequence of parentheses. How many people follow this analogy? If I have an incorrect sequence of parentheses, I have more closed than I have open. So what's the bijection? You were saying the open parenthesis is the same as the move
To the right.
to the right, and the closed parenthesis is the same as
Move up.
move up. This is a function that takes any path, makes a sequence of parentheses out of it, but also the other way, I can take a sequence of parentheses, make a path out of it. Because just I replace the parentheses with moves up and right. If this is a correct sequence, the path must stay under the diagonal. It could touch it occasionally, could be equal number of closed parentheses and open, right? Like in here, would I touch the diagonal here? Open, 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 close, close. Do I touch the diagonal? No. Open, close, close. No. But at the end, of course, I touch the diagonal because in here it's the diagonal. So how many total ways to put correct parentheses are there? If this is a bijection function.
Yeah.
Number of ways is the Catalan number, which is 1 over n plus 1 to n choose n. Because we have a one-to-one mapping between those two problems, we already know the answer to this one. So we have an answer to that one. There are about 400 problems that have an answer similar to this. And a large chunk of mathematics, discrete mathematics, and computer science recently has been devoted to how do you figure out, based on one problem, how to solve the other problem. That's how also computer science is proof that problems are very difficult. If you heard of this P versus NP kind of question, NP means problems that are not solvable quickly. How do we prove a problem is not solvable quickly? We do something like this. We say, if this problem is not solvable, and this is at least that hard, then that must be not solvable. Can't be if they have equal difficulty, not size. I'm making an analogy. If they have equal difficulty, and I already know this one's hard, that one's going to be hard too. So that's a famous Cook-Levin theorem that allows us to think of these NP-complete problems that way. If we know something is hard, this other problem can't be easy because solving this would solve the hard one too. RSA goes like that. The way you prove RSA is hard, you show that if you could break RSA, you could actually do all kinds of things that we know they're hard. Okay, so that's the second problem. How many ways can you put parentheses such that they correct? Is that number. A third problem that I want to talk about is in how many ways can you multiply things. So what I mean by multiplication is, you know, if I have A, B, C, D, I could do it in several ways. Let me say here, I can do A times B times C times D. I could do A times B times C times D. I could do A times B times C. Sorry, no quote here. Times D. I could do A times B C times D and then multiply them together. Or I could do A times B times C times D. So that's the ways, order of multiplications. In most algebras, like the algebra we study in high school, no matter how you do the multiplications, you get the same answer. Modulo algebra, the same, right? If you take modulo 25 and you do the multiplications in any order, you get the same answer. Linear algebra with matrices, the same thing. You have a bunch of matrices to multiply, you get the same answer no matter the order. Some algebras don't have this property. The way you multiply them, you get different answer, but most algebras do. The real problem here is not the answer. Why would people bother to care about in what order do you multiply them? It's not because of the answer. The answer is usually the same. It's because of speed. You're going to do this for matrices. It will matter a lot which matrices get multiplied first. Because the size of matrix will say if you multiply something that has fewer inner columns, rows, but a lot of outside ones, like 100 by 5 times 5 by 1,000, that'd be a huge number of multiplications. But if you figure out how to do them, how to align properly the matrices, you're going to study that in algorithms. You're going to do much less computation. So the issue here, why people care about this kind of problem, is how to do it fast. How many total ways to multiply matrices or numbers or remainders modulo n are there? The same number like in here, and that may appear very intuitive, right? The way to put parentheses should give an immediate way to multiply things. Seems like a very common sense thing, right? Every way of multiplying thing has to do the way of putting parentheses. And that is true, except the function is not that quick to find. You try to do this. You say, okay, every way to put parentheses, how many parentheses I have here? Four pairs, right? How many parentheses I have here? 3 pairs. So this multiplying 4 things doesn't correspond to 4 parentheses, corresponds to 3 parentheses. So this has to correspond to a 3 parentheses, n equal 3. So I have 3 sets of parentheses. But how do we build a mapping? I think intuitively should be a mapping between all ways to multiply things and the ways to put 3 sets of parentheses. However, that mapping, I'm telling you, is not that trivial. So I'm going to leave this as an exercise for you guys to figure out and talk about it later on. How do I go by? If I tell you, take for granted that every way from here corresponds to a way from here of putting 3 sets of parentheses. Can you build me a bijection function? Literally, that takes one of these and creates, let me give you one. I give you as a pointer, which one is this one? A, B, C, D. There's a parenthesis missing here, I think. There's one before B. This one will map into open, 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 close, close, close. So I want you guys to find a rule, mechanical rule, that says take every literal, move it around, take the dot, do something. If I give a string like that to produce a string like this, such that this is a bijection function. And it should work not just for 3. If I can do it for 4. This will be corresponding to ways to multiply 5 things. So by having such a bijection function, which we're going to come back to in about 2 weeks, I also get that the number of multiplications of things, it's also the Catalan number, just the one before. It's not Cn. This is Cn minus 1. Because it's not for 4, it's for 3. Now, that's what I have on these numbers for now. Once we're done with the midterm and probabilities, we're going to see other problems that have Catalan numbers. Remember the first day recitations, before even the first class, I gave you a paper with a bunch of triangles on it. And I asked you, how many ways can you take that polygon, break it into triangles? Is that not way? But to get to triangles, we need more theory. We can't simply do the bijection. We need something called recursive relations. So when we study that a month from now, we're going to get back to triangles and prove that the ways to do triangles, it's also Catalan number. But we can't do it with a simple bijection. For those of you that are curious, this paper posted online explains how to do that, or you can wait 3 weeks or so for me to do it in class. There are many combinatorial problems, counting problems that rely on these numbers. So now I want to do one more fancy, let me put it here, one more fancy problem before that concludes the counting, and then for the rest of the lecture today I'm going to do midterm problems. Obviously this is not going to happen, the midterm, nowhere close, right? So I'm going to do one more example that's part of the fancy stuff, and then we'll be back to reality, which is tomorrow you guys have an exam. This problem appeared in the International Math Olympiad. Those are these crazy people who do just math, right? So this is what it's saying. I have an equilateral triangle made of unit triangles. The way this goes is there's an equilateral triangle. I think I have here 1, 2, 3, 4, 5. So I'm going to draw here n equal 5. And then I don't know if I'm going to get this right. You guys know that if I take an equilateral triangle, I can break it into triangles this way. See, this is supposed to intersect here. Doesn't really intersect. I can do this for any n, right? Because if I want to do n plus 1, I just add up one more row. And that will be the n plus 1 row. And then by building this, I get to the next row. So I only want to do n equal 5 now, but I'm saying if I would do n equal 6, it just adds one more row. All these equilateral triangles are the ones with equal sides, and the angles in them is what? How much is 60 degrees, right? So they all match up perfectly here. Here's the problem. You start here, path. So the problem is, again, we start in here. And the way we can move, this is like starting position. It's got to move here, then it's got to move here, 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 here. Then here, here, maybe, then here, and here, something like that. The rules for those paths, it's got to start here. It's got to go, don't go up. So you can't go up. But you can go sides. From here you can go this way, and from here you can go down. But you have to end up on the last line. So you got to end up in here. That's a stop. I think you could have ended up here, maybe. And you have to cross an edge at every move. So you see how my path cannot go through a vertex. Every time it moves from here to here, it crosses one of these unit edges. Every time it moves from here to here, it crosses a unit edge. So in order to move to the other triangle, you gotta cross an edge. You can't go through the vertex. How many people follow me? Good. So what's the question in all these problems? How many paths? This is a difficult problem. Not because what I'm going to show it to you is going to seem simple, but it requires creativity. Creativity in mathematics is a very precious thing. People who are really get prizes in mathematics are the creative ones. Question? Yes?
Well, isn't it just like a Pascal's triangle?
What?
Isn't it like a Pascal's triangle?
Right, so there's obviously different paths, right, to end up in the last row. It's not just a unique path. I could have gone here and here and here and that. Is that what you're asking?
No, Pascal's.
It's not. So I'm going to show you how to do such a problem. We want to build a bijection function that takes every path and does something with it. We're going to map it into a sequence of numbers with the condition that A1 is 1. I'm going to write it this way. It really means A1 has to be 1. And every other one is smaller than its index. So A2 is got to be 1 or 2. A3 is going to be 1 or 2 or 3. All the way to AN, which is going to be from 1 to n. So these sequences have a certain property that is there are n numbers in there in the sequence. And this one is 1, this one is 1 or 2, this one's 1 or 2 or 3, this 1 or 2 or 3 or 4, and this guy is 1 or 2 or 3 or 4 or up to n. So I want to build this function that takes such a path and processes a sequence. And to show it's 1-to-1, I have to reverse it. I have to say, okay, from a sequence, you also get a path. Remember, 1-to-1 functions have to go both ways. So I is going to be my bijection here. Is the moves, the number of moves on that row until path goes down. So what I'm saying, you see how path comes in? Has to do a bunch of moves until it goes down. Like on this considered the row here. The path came in here. It's gonna do a bunch of moves, one, and then it's gonna go down. But it could have done 1, 2, 3 moves before it keeps going down. So AI is gonna say, once you go into the row, how many steps you make on that row before you go to the next row. Goes down to next. So that's my bijection. What you have to prove at home is that this goes both ways. For every path, obviously I have to do a bunch of moves because I can't go immediately down. Once I get in here, if I try to go immediately down, that'll be a vertex. So I have to make at least one move on that row before I decide. And I have to figure out why can't I go left or right. That's another thing. But then the thing that I want you guys to think about at home is, if somebody gives you a sequence, can you uniquely construct a path? You know you're gonna start here. You know the first move is gonna be down. And then this AI should tell you, should I go this way or that way? And should I go how many times? If I end up in this row, how many units I go on that row before I go down? That's what AI is. So try to build this construct. That's an exercise, extra exercise. Why is this, how is this big bijection gonna work? But now, suppose we build that bijection. Can we count this? The purpose of building this one-to-one function is to say, okay, I know how to count this. How do I count this? How many sequences, if this is 1 and this is 2 values and this is 3 values and this is 4 values, all the way to n, which is n options. And every option goes to every option, right? Any A2 goes to any A3, goes to any A4, so on and so forth. How many total sequences are here? Yes?
And factorial?
1 times 2 times 3 and factorial sequences. This is just the product rule that you study in class. If there's 1 option for this and 2 for that and 3 for that up to n, then I have n factorial options. So how many paths are there? N factorial paths. Assuming you guys can prove this is a one-to-one function. How many people follow me? That's where we're gonna stop with this counting theory. So now we're done with counting. You guys did everything and much more that's in the book, and much more than the regular section. But for the second part of today's lecture, I want to go through some more down-to-earth problems, not Catalan numbers. So I have a bunch here. Let's see. Some of this stuff is really easy. You're gonna be like, okay, after you show me all this fancy stuff, are you kidding me? You're gonna take me down to play license plates with digits and, okay, well, that's what's gonna be in the midterm. License plates with, I don't know, passwords and phone numbers. And, I want to make sure you get some practice on this. But before tomorrow night at the midterm, please look at this summary page and the recitation for next week. Okay. Here's a bunch of problems. Diagonals on antagon. Here's an antagon. I don't know how many vertices I'm going to end up with here. 1, 2, 3, 4, 5, 6. How many vertices I got here? 8 maybe. So n vertices and edges. We can call the vertices from V1 somewhere, V2, V3 up to V7, V8, 4, 9. The question in here is how many diagonals? What's a diagonal?
A line connecting two vertices.
Any line connecting two vertices?
Straight lines.
Straight line, but some of them are not.
That isn't an edge.
That is not an edge. So these are effectively pairs VI, VJs, right? That's a line connecting two vertices. Except things like VI and VI plus 1, except edges. Edges don't count as diagonals, but these will count, right? And this will count. Any other edge does count as diagonal. So let's not waste our time. Too bad. How many are there? How do I mean, if you get this from the meter, you have to be able to do it in under 100 seconds. That's kind of the speed of the meter. Because it's a very simple problem. How many diagonals are there? Or how do I count them?
6 choose 5.
6 choose.
5.
Okay, where is this coming from? Why is 6 choose
Oh,
5?
wait, 1, 2, 3, 4, 5, 6, 7, 8. 8 choose 7. Sorry.
8 choose 7.
Is that?
So you're saying I pick a vertex,
or no.
right?
No, then-
I pick a vertex.
No.
That's our thinking. I pick a vertex.
Yeah, pick a
And
vertex,
then
and then you have
where can I do diagonals from this vertex? Right? I can go to all places except where?
Yeah, so
The two
it's
next
8
to it
choose
and itself.
Yeah. Oh, choose 5.
Okay? You guys follow me?
Keep trying.
If I pick this vertex, where can I draw diagonals? To all the other vertices except itself and except the immediate neighbors. Except the immediate neighbors, why? Because if I draw to immediate neighbors, those are edges. So what is this number here? It's not 7.
No,
I
it's
think
5.
It's 8 minus 3.
Sorry.
Meaning in general it's n minus 3. That is choose a vertex and draw n minus 3 diagonals. That's it? Or do I have to do stuff? Is there a problem here? Yes.
Multiply by the number of points there are. So multiply by 8. Because this is the number of diagonals we draw from one point, or from one vertex.
Right. So what is this saying? From one vertex, I pick this vertex, I draw the diagonals. How many ways can I do that? Is that really true? That's why I'm asking, is this number the correct ones? I think you got the right idea, but it came out wrong.
Okay.
Because I think he's saying multiply by n. So let's fix this idea first. I pick a vertex and I draw how many diagonals? N minus 3. So it's not this. It's just n minus 3 diagonals
Into the number.
for a vertex V. Right? I pick a V and how many there are? N minus 3. You know what you're saying? That's for one vertex. But I could pick any other vertex. So what do I do?
Factorial.
By the number of
Multiply by number of vertices. This is choices for V, right? You guys follow me?
Yeah.
I choose a V. How many diagonals are from V? N minus 3. And then I say, how many ways could I have chosen this V? N ways. N?
Because
Louder, please.
that gives you duplicate, because if you start with like V2.
I've counted every diagonal twice. Once from V5 and once from V2. That's the same diagonal. So now I do what? This is a tricky point in a lot of combinatorial problems. When the guy asks you, count the diagonals. Do you mean count a diagonal from V1 to V2, but also as a different diagonal, as a different pair from V2 to V1? In here, because it's diagonals, it means no, only count them once. So then you gotta take out the duplicates. But in some problems, if I say count me the pairs, generally when I ask for a pair, AB pair is not the same as BA. So that counts as two different pairs, right? How can I have done this differently? How about I choose all pairs? Isn't that all the possible lines? I'm counting the diagonals, and I'm saying the diagonals corresponds to pick any two vertices, gives you a line, minus the ones that are not. This is all lines. Which one I have to take out? Yes.
8 lines?
The sides,
All the edges, yeah.
minus the sides. So how many are there for n? If I have n points, how many edges are there?
N edges.
N. Is that the same as that? Okay, we just spent 5 minutes on a problem that's supposed to be 90 seconds. Just to give you a sense of timing. Next one. How about referring to these diagonal thingies that it's counted twice? What if I say I have 10 packages and I want 10 packages, say £1 each. I want a partition into a set of 5, package 1, 5 packages, and another set, which is subset, another 5 packages. How can I get out of 10 packages 2 sets of 5s? How many ways? I have 10 identical packages that those are like, identical phones, and I want to group them into a set of 5 and another set of 5. How many?
10 choose 5.
10 choose 5, but what should ask yourself if you have the same problem as here? When you say 10 choose 5, it's choosing 5. But I can choose those 5, and the remaining 5 are the other subset. At some point later on, you say choose the other 5. Didn't you get the same partition? So you should ask yourself in terms of the result, is when you put the partitions, do you matter, does it matter? Am I counting stuff twice? In fact, we should make a quick recap here of those rules. What do we ask ourselves in counting? Did I count everything?
These ones don't count. Choose all the ones. These ones don't count.
Did I count anything twice or more than twice? Did I miss some? Is the result a set or a sequence or what? Is a mask for an ordered things on unordered things? And is result duplicated, out of order? There are probably more questions to ask here, but everything where you count, you ask, did I miss any possibility? Do I count something twice? It's in the intersection. In here, when I produce 2 sets, are those sets produced multiple times? In the diagonals, did I multi-count the diagonals or not of the other one? You gotta ask yourself these questions, even if it's obvious from the text of the problem. Always ask yourself, did I miss anything? Okay? Next problem. Next problem is ball into beans. Some variations of that. So how about books on continuous shelves? On shelves. Books sorted in order, sorted alphabetically. So here are my shelves. So I have n books on k shelves. What does it mean for the books to be in order? And how many ways can I put the books on the shelves? I have those books. They gotta be in order, sorted by the author. And I have to put them on k shelves. In how many ways can I do that? This is the same problem you had in the homework 3. The deal here is that the order implies the books act like what?
Balls.
Balls. Because order implies only counts matter, right? Once I have the counts for each shelf, I know exactly what books are going to go where. So how many ways to do so? Number of arrangements on those books on shelves is what? N plus k minus 1. Good. But now, what if all shelves have at least one book? Is the original spreading of books into shelves or balls into bins can have 0 counts on some bins? Right, I'm saying that's not possible anymore. You can't have empty shelves. What do you do now? Yes.
So first you sort them in like one book each.
Right, they sorted already and they have to stay in that order. The problem with order still is there. You can't move them out of order, but you cannot have empty shelves. Some of those balls into bins will end up with the second shelf being empty. Right? That's not allowed. What do you do now?
So you subtract like the number of shelves. Assume that like they're already.
So subtract 1 for each shelf. Then what?
Do the same thing.
Do what? The same thing. Do balls into bins, but with what? How many balls?
The remaining books.
Huh?
The remaining books,
Which are?
which are so n plus n minus k,
And how many bins?
and n plus k minus. Wait, oh, n k minus.
Still k bins, right? I still have k shelves, but I have n minus k balls because I saved a book count of 1. I don't know which book I saved, but I save a count on 1 for each shelf because that's a guaranteed thing. Each shelf must have a count of 1. So that's k books. And then when I do these balls into bins, I get how many ways? How do I do balls into bins for n minus k books now? I save a count of 1 for each shelf, which is the minimum that I need for a shelf. I split it into k bins. So what is n minus k balls into k bins?
Minus k plus
Minus k plus k minus 1 taken?
k.
Minus 1. Now for each way, each balls into bins counts. From n minus k balls to k bins, how do I get the actual count on shelves? Count on each shelf. So once somebody throws those books into shelves this way, how do I go back and say, what's my real count of books on each shelf? Remember what I did in the first step? What do I do back? Now I have to do something about this 1. Yes.
Like those one book that you left on each shelf, you could permute those in any way.
You can't permute the books, they're in fixed order. What I'm saying, suppose the counts in here, this is one such example. Suppose it counts, for example, as the counts come as 1, 2, 0, 2, 0, 3, 4. Now what do I do with those counts? I add back the 1 that I saved initially, right? The actual counts on book on shelves will be 2, 3, 1, 3, 1, 4, 5. So I reserve this 1 count for every shelf because I have to have at least 1 book for each shelf. So I save that. Now I throw the balls into bins. Counts can be 0 now or not, who knows? For every count I add 1 to them. That's the book I saved initially for each shelf. And those are my counts, how I put the books on shelves. The order stays fixed of the books. So as soon as I have counts, I know exactly what books will go on each shelf. The first 2 books go on the first shelf, the next 3 books, so on and so forth. And why I can have 0 here? Why am I guaranteed now to not end up with empty shelves? Because no matter what happened, I added 1. So every count now, it's at least 1.
So you just add k back to the formula at the very end?
Because I need to put those K books anyway back.
Yeah.
And I save them because I know it's going to be 1 per shelf. Right? How about
So you have to write k, so you do the formula.
I added +1 on each shelf here?
No, yeah, I mean, this is the actual number of combos though.
No. These are the same number of combinations. That's my point. This is a one-to-one function. Every throw of balls into bins from here corresponds to a valid count. And every valid count corresponds to a throw of balls into bins. So this is the answer. Which was the balls into bins thrown after I took those K books out, which were the saving counts to make sure I have one book per shelf. Who followed me on this? Okay. The principle is still balls into bins, but I need to save this one count for its shelf in advance, because if I throw them without saving that count, I may end up with empty shelves. What if I want to say, here's an alternative version of this problem. I don't say not empty shelves, so I say still books on shelves like before, but I want them the non-empty shelves to be continuous from shelf 1 to shelf something, J. So what I'm saying is, people when they put their books in the library, they populate the first shelf, right? And then they put some others on the second shelf, and then some other books in here. Could be more or less, right? And then, but then the empty shelves are at the bottom, right? All those balls into bins in here, I assume you can throw the books in any way you want. I'm saying here I can have empty shelves. So empty shelves, empty, at the bottom
Or top.
or top. How do I do this?
You want the two empty shelves,
Right, I can have empty shelves,
and you want at least one of them to be.
but I want the number of ways to arrange the books on the top shelves until up to some point, and then the bottom ones to be empty. How many ways can I do that?
How many bottom of that kit?
That's the key. We're gonna split into cases, into counts by non-empty shelves. Let's say they're J. So if you count them, shelves 1, shelf 2, this is shelf J, that's the last, this is J minus 1, that's J. That's the last shelf that is, this is empty, and this is empty. No, that's why I'm saying continuous. The books have to flow non-empty shelves up to some point, and then you have empty shelves. If I call this J, am I back now to the previous problem? Didn't I just say how many ways can I distribute my books on J shelves that are non-empty?
Yeah.
So I know that count is what? How did I solve that problem?
And plus K.
Distribute my books on J shelves continuously. Didn't I just solve it in here with K instead of J? So that's N minus J plus J minus 1 on J minus 1. That's how many ways I can do it on J shelves. But I split into cases. This is a partition, right? Because J shelves not the same like J plus 1 shelves. There's a case with populate 3 shelves, and another case would populate 10 shelves, and another case would populate 5 shelves. So the answer is, since I use partition in the beginning, I have to sum up those counts. Sum for all possible J's from 1 shelves to how many you have of N minus J plus J minus 1. This is due to the partition which says you count those things separately. This is in how many ways can you do it with 1 shelf? Then how many ways to do it with 2 shelves? How many ways can you do it with 3 shelves? So J is the number of shelves that are non-empty. Each one of these is separated at disjoint cases, because if you arrange the books on 3 shelves, will never be the same as arranging the books on 10 shelves. So then you add up with counts for each one of those cases, and you add up the counts. It's a typical partition thing. When we say we want to count something, we break into partition into several disjoint cases, 1 shelf, 2 shelves, 3 shelves, 4 shelves, up to how many shelves you have. Each one of them is a separate sub-problem that doesn't intersect with the others. We count, we just did it here how to do it for K shelves, so we do it for 1 shelf, 2 shelves, 3 shelves, 4 shelves, and then we say the number of possibilities, it's all those counts add up, the sum rule or partition.
How would you be able to do that quickly?
This counting problems is not a matter of doing the calculations. You're going to leave the answers this way. So we're not asking you to come up with decimal numbers. All the counting problems can be left into combinations, permutations, factorials. Don't bother trying to get factorials out because you get no points for that. In fact, you make it harder to read for the grader. When you say count something, you can end it up like this.
In this problem, are we guaranteed that the empty shelves are at the bottom and not at the top?
Right. If you want to consider that, there's more cases.
Yeah.
But what I'm saying is you need to break into cases that are disjoint and then apply this thing for each case.
Oh wait, so we're doing this without, we're saying that only the bottom shelves can be empty,
Yeah.
but not top.
Yeah. Because then there'll be another cases when you fill it from the bottom. Those would be different cases than the ones you fill from the top.
So do we just multiply by 2?
Yes, I think it's the same. Any arrangement from the top can be seen from the bottom, except if you populate all shelves, now you've counted something twice in that case. When J is the maximum, you probably counted twice from the bottom, from the top. Let me give you a variant of this problem, very related to the actual time of the year. What if I have n Halloween candies? To K kids. How many ways can I distribute with candies to kids? I have n Halloween candies and K kids, and they all come begging. So what do? How many ways to distribute? Those candies are in here. Identical. The books are not identical, right? But what makes the books look like balls?
Already permuted.
Fixing the order. In here, candies are identical. That's all the candies are the same. There's no IDs. That's another thing you should ask yourself here. What or who has IDs? By IDs I mean, is there a candy 1, candy 2, candy 3 in this problem? No. Those candies only have counts. You can tell how many there are, but you can't distinguish them. Is there a book 1, book 2, book 3 in this problem? Yes, but they are fixed in order. That's the same like the problem in number 3, right? You got the sequence, they are clearly distinguishable A, B, C, D, F, G, but the fixed order make them act like balls. You guys follow this? The balls into beans is like a 99.999% to show up in the meter. Just to make sure that if you're still struggling with this, look somebody for office hours today and tomorrow, come to recitation, do something with those balls into beans if you're not comfortable with it, because that's going to show up. How about here? What's the answer? How many ways can I distribute n candies to K kids?
And minus K plus 1.
Plus K minus 1 into K kids, right?
Wouldn't it be K minus 1? At the bottom?
Yeah. Wouldn't it be nice that each kid gets at least 2 candies?
Yeah.
That's a nice thing to do for Halloween. Each kid, at least 2 candies. Then what? What now? How do I solve this problem? I need to guarantee that every kid gets 2 candies. So what do?
Minus 2K.
Save. What kind of count I need to save? 2K count. Those are the ones that are like effectively I have to give away 2 for every kid no matter what. I don't know which candies, but it doesn't matter. Candies don't have IDs. So I save those 2K. Those are 2 per kid that I need. And then I do balls into beans for what kind of, how many balls I have?
And minus 2K.
N minus 2K, how many beans I have?
K minus 1.
Still K beans. I still have K kids. Right? So what's the count? N minus 2K plus K minus 1. K minus 1. That's the answer. The reason is that's the answer is that if I add now to whatever counts come out here, when I spread those balls into beans, I take those counts. How do I actually decide how many candies I give to each kid? If the count here is, I have 4 kids, 1, 0, 3, 2, say, I get those counts. When I spread the balls into bins, how many candies every kid gets now? The first one will get how many candies? 3, 2, 5, 4. Because I put back those 2 candies that I saved in the beginning. Do kids have IDs in here? Is kid 1 different than kid 2? Bins, do bins have IDs? So is this different than 1, 3, 0, 2?
Yes.
Yeah, kids do have IDs. Okay, so this throw of the balls into bins is not the same as this throw. Looks the same, but it's not. Right? So you gotta ask yourself about these results. Hey, I get this throw, these counts into bins by people being partitioned or whatever. Are those the same thing, or I'm counting something twice here? If those would be the same thing, if somebody asks, I don't care who's the kid that gets 3 candies. To me, this distribution is the same as this distribution. That's a reasonable thing to say. I'm the distributor of M&Ms. I say, I don't care who's the kid 1. I only care about the possible distributions. In each case, this is the same thing. How many times I overcounted this particular sequence? Then. And how many ways can I get these particular 4 counts into, when I do balls into bins? 4 factorial. All the throws of balls into bins will have these numbers 4 factorial ways. How about these numbers? 1, 2, 2, 1. If I count distributions, I don't care which one's kid, is it still 4 factorial?
Divided by 2.
It's not 4 factorial because the counts 1, 1, 2, 2 will not gonna appear 16 times or 24 times because they're repeating counts. So you gotta ask yourself these questions when you count stuff. Okay. Next. How about I have 8 people sitting at the round table? Now, the arrangement here has to do only of who is the neighbor. Left and the neighbor right. So, what's the difference between a round table? I have 8 people with 8 chairs, and a sitting on a row in a classroom. So I have 8 chairs and 8 people. First of all, if I have 8 chairs and 8 people, how many ways can I place those 8 people on 8 chairs? Order matters or not?
Yeah.
When I say 8 people on 8 chairs, do I mean, does it matter the order? Of course. How many ways to place 8 people on 8 chairs? 8 factorial ways, because the chairs are fixed. Any permutations of people goes on chairs. What is different here? In here, we're not putting people on chairs that we count. If we assign IDs to chair 1, chair 2, chair 3, it'll be the same problem. In here, we only care about who are my neighbors. So at the table, if I take a particular table, say this is the person 3, this is the person 8, this is the person 6, this is the person 2, person 1, 5, 7, which one did I miss? 4. This particular arrangement, if I rotate everybody 2 chairs, it did the same arrangement on the table. Because on the table, round table, only matters who's in my left and who's in my right. Doesn't matter what chair I'm sitting on. So obviously there are not that many, there are not 8 factorial ways to put people around the table. Because some of these ways are the same actual arrangement. How many ways are there? I know some of you came on Sunday and we discussed this problem. So people who did not come on Sunday, how many ways are there? You came on Sunday? Okay, somebody who didn't come on Sunday. How many ways to put 8 people around the round table? Well, I don't count different ways for different chairs. I only count different ways for different neighbors, left and right.
Factorial?
Why?
Because we remove every single possible starting index if you're counting.
So there's two ways to think about it. One way is like he said, since I can rotate the table without changing the arrangement, I can fix this guy on this chair. Effectively remove the index, rotate the table until this guy ends up in this chair. Rotating the table doesn't change the arrangement, right? We just said that. So I can take any arrangement and rotate it until person 6 ends up in the 3 o'clock kind of thing. Then the table does not rotate anymore. This serves as a reference point. It's not a choice. I'm not choosing anything. I'm only saying I want to look at any arrangement with person 6 sitting there. If you are uncomfortable rotating the table, you can rotate your head to get that person at 3 o'clock. If rotating the camera, it looks different, but it's the same arrangement, right? So because arrangements can be rotated, what he's saying, I'm going to fix the point of view so all arrangements are not rotatable anymore. I'm going to, whatever person 6 was, rotate the table to end up in. Doesn't change the arrangement. Now, how many options I have for the other 7 guys? That's where the 7 factorial comes in. I can put 7 people on 7 chairs in 7 factorial ways. And now tables do not rotate, so all those ways are different. Make sense? Hands up, who follow this? Good. I can think in a different way. I could take all A factorial permutations and say, how many times I overcounted each arrangement? Each arrangement has been counted. All the ways I could rotate the table and have the same arrangement. In how many ways can I rotate a certain table without changing people on the chairs? How many ticks are there on this table? 8 ticks, right? So I can rotate in 8 ways. Every possible arrangement has been counted 8 times. So if I want to say the number of arrangements is all the permutation divided by the overcount. How many times I counted each one of them, right? That will give me 7 factorial, right? The same number. How about if I have 8 Christians? That's 7 factorial ways to put them, right? We already figured that out. And I have 8 Muslims. And the condition, every adjacent people have different religions. This is one of these debating tables where people try to figure out what they're going to do next, you know, nicely at the table, that's what I mean, right?
Yeah.
And they sit at the table and they say, okay, let's mix up. Let's not sit 2 Christians or 2 Muslims next to each other to encourage debates, right? I'm not religious. This is mathematical example. So how can I do this? Place 8 of one kind and 8 the other kind such that they interleave. If I wouldn't have the interleaving condition, in how many ways can I place 16 people at the table? So let me ask again, if I don't have this condition, I only have 16 people, how many arrangements are at the table? Did we just solve that problem?
Yeah.
15 factorial. Now, if I put this condition, you're saying you have the answer?
Yes,
15 choose 8? I don't think that's true. But let's see. First of all, I can put the Christians in 8 factorial ways relative to each other. I know they can't see next to each other. Why is 15 choose 8? What's the thinking? You're saying you pick 8 spots out of 15. That's 15 choose 8. But those 8 spots could be next to each other, right? Which is a problem violating the condition of the statement. Yeah. I can't have 2 Christians next to each other. So how do we think about this? Yes?
If you put one group first, say the Christians, that would be 7 factorial, and then
Stop right there. Put one group first. That he doesn't say on chairs. It says relative to each other. Establish a sort of what's my Christian on the left side. Maybe it's not the next chair, but it's at some point on the left side there is another Christian. And then what's the one on the right side? So put those first. And then somebody else. Once I have the Christians, what are my choices now? to distribute.
Distribute the 8 Muslims in the slots between the Christians.
How many options are for that?
8 factorial.
So I put the Christians first, that's 7 factorial. Muslims in the spots between. Why is this 8 factorial and not 7 factorial like before?
Because we already fixed the point of it.
I already fixed the point of reference. The tables don't rotate anymore now. So I have 8 people for 8 spots in between 8 factorial. Your recitation paper contains an advanced version of this problem. That's harder. So there's this problem and then an advanced one. Let me see here. We have time for some simple ones. On my notes. Halloween candies, we did that one. Yeah, so let's try to do 4 problems in 8 minutes. See if we can do that. Just get the answers. I have 6 Rihanna songs and 5 Beyonce songs. And I want a playlist. I can't write. Of 8 songs for each. Playlist, order or not order? When somebody says playlist, order. How many ways to choose 4 songs from Rihanna and songs from Beyonce out of my collection there and put them in an order?
64.
First I have to choose.
Choose places to put the song.
Choose like any 4 Rihanna songs.
First I have to choose which Rihanna songs I'm using, right? Say, for example, that's 6, choose 4. And then,
Put them in the line.
is it choose 4 or permutation 4? So you have to think of the, here's my playlist. I have to choose a bunch of things. If I say choose out of this permutation 8, 4, this is positions for R songs. Right? Is that a set? Just choosing the positions for Rihanna songs. A set or a permutation? Set. Then I have to choose 4 songs in order from Rihanna's playlist. That is permutations of
4.
6, choose 4. And then I have to fill the other 4 positions in order with Beyonce songs. Is it this times that times that? Is it any choice with any choice with any choice works? Yes. How about phone numbers? Seven spots. Here they are. Exactly. Let's condition. 1, 2, 2s, 3, 3s, and some other digit. Right, because 1 position plus 2 plus 3 doesn't fill the phone number, right? There's still 1 position left. How many ways can I do this? How many ways can I choose where this one goes?
7 choose 1.
7 choose 1 possibilities. How many choose I choose and how many ways this 2 goes? 6 choose 2 possibilities because I only have 6 spots left. How many ways I can choose where 3 3s goes?
4 choose 3.
4 choose 3 possibilities. Do I still have positions to choose?
No.
After I choose those, there's 1 spot remaining. That's the spot. I can't choose the spot, but what can I choose?
Number.
The digit. How many options are for the digit?
10.
Not 10.
7.
Why the not 10? If I choose a 2, what happens if I choose a 2? I got 2 occurring 3 times, but it says exactly 2 times. So I can't choose a 2, so I choose a digit except 1, 2, and 3. That is 7 possibilities. So it's that times that times that times 7. Again, the problem here is overcounting or undercounting stuff. Choosing, many people say 10 digits options here, but some of these options are invalid because choosing another 2 or another 1 or another 3 will give the counts of those too many. See, one more. Um, 8 character passwords. They in a set AZ, small, 0 to 9, the digits, and some specials like asterisk, underscore, so on and so forth. Those are 12 specials. Those are digits, they're 10. Those are small letters, they're 26, and those are big letters. They are 26. So how many total things are in my set there? How many possible choices for characters?
74.
74. So now there's a condition, at least, or constraint, at least 1 digit and 1 special. And 1 special. So this is an and. Repetitions allowed. How do I think of this problem? I can take all passwords minus the ones that are bad, the invalid ones. How many passwords are there? Total? 74 to the 8. Minus the invalid ones I'm going to write as a union. How can somebody be invalid? What does it mean invalid if the problems ask me you got to have 1 digit and 1 thing? What makes a password invalid? It has either no digits or because it's a negation of n, right? Or no special. What is this or? What does it mean? Union. So it's, how do I need the size of this union, right? How do I do the size of a union?
Inclusion.
Inclusion, exclusion. So that would be subtract the size of no digit, subtract the size of no specials. Now, are those just disjoints? Does a product rule apply? The sum rule applies here?
No, because they
No, they have intersection. So what do I do intersection? I have to add the intersection no digit and no special. How many passwords have no digits? They can be anything but not digits.
14.
Everything except digits to the power 8, right? That's the same like before. So how many are there?
64.
64 to the 8. How many passwords have no specials? 62 to the 8, because it's excluding the specials, I get 62 characters. How many passwords has no digits and no specials? Can you do this in 4 minutes? That's what the midterm effectively is asking.
Can we also do it using that, like the way we did this one?
I'm not sure, but again, you gotta pick something that you know for sure is gonna work if you start trying stuff. Yes?
Yeah, so going up to what she said, so I see
I'm not sure.
one area needs to one
But